Thanks, everyone. I know we only have 45 minutes for lunch, but this means that we will have more and longer breaks in the afternoon to talk about all the interesting ideas that Dr. Fernandez has this afternoon sessions. So I had the pleasure of working with Dave at Sun Microsystems, where he worked on the ZFS storage appliance. And he's today here to tell us about ZFS in the Manta storage system from Joyent. So thanks, Dave.
Thanks, Matt. As Matt said, my name is Dave Pacheco. I'm an engineer at Joyent, and I'm going to be talking today not so much about ZFS internal, but about a system that we built at Joyent called the Manta storage system, and the way we use ZFS in it, which I think is what people will find pretty interesting. So the first question is, what is Manta? How many people here have actually heard of Manta already? Okay, that's pretty good. How many people have actually used it? So the idea behind Manta is to scale the Unix philosophy of big data, which is a whole bunch of buzzwords. So, okay, let's take some of those things apart. Unix philosophy. I think this crowd probably gets this already, but I think this is a really compelling example. Has anyone seen this example before? Use this when we're talking about Manta. In 1986, John Bentley of the ACM asked Don Knuth to write a program that demonstrates literate programming. And the problem with this one right here, very straightforward, turns out to be a very good problem for this question, which is, given a text file in an integer k, there's the k most common words in the file, and the number of their occurrences in decreasing frequency. So Knuth comes back with a solution that's 10 pages in a custom programming language, which is fine, it's the point of the article. But Bentley then asks Doug McIlroy, famous for inventing the Unix pipe, to review this solution and talk about it. And he comes back with this shell pipeline. He literally replaced Knuth's programming with a small shell pipeline. And he talks about, he's talking about Knuth's solution in the context of which literate programming was supposed to be about, comment describing the code that's going on. Fine. But there's a deep value in something as simple as this, which is that the pieces of this are very composable, and it itself is composable to build larger programs. That's why the shell is such a compelling way for people to interact with the computer, because you can iterate really quickly, right? You can be like, grep whatever, oh crap, that matched too many things. I'm going to grep some slightly different thing, or some slightly different set of files. Oh, that wasn't quite right. I need a different set of files. You can keep iterating, right? The goal with Manta was to be able to take this same approach, but apply it to a workflow on data that was much larger than can fit on a single system. Right? That's kind of the working definition we use for big data. It's data that doesn't fit perfectly on your laptop, on a server, on a single system. It actually dovetails very well with the question about scaling out ZFS, like scaling out horizontally. What does that mean? And the conclusion we came to was that the answer to that is not necessarily just something that looks like a file system that's distributed across multiple systems. We made a very different choice informed by some of the distributed systems work, which I'll talk to in a little bit. I already talked about this. So just to be clear about this, though, the Unix philosophy that we're talking about is not just about the tools, set, off, grep, sort, things like that. It's actually an approach to building programs that you can apply to anything, Python, Perl, C, Java, etc. So fast forward to 2004, Google puts out the MapReduce paper, which is a seminal paper in so many ways in distributed systems, and it's all about distributed computation. And what is the problem that they use as an example of the distributed computation? Well, it's actually the exact same problem. It's couched in terms of web page requests from a server access log, and producing a count of the URLs accessed and decreasing frequency, whatever. And this too is obviously a natural fit for a MapReduce pipeline. If you look at the original pipeline from Doug McIlroy, you have a phase which is clearly mapped. It's the thing you're applying to each of your input files. And then you have a part that combines all the results. What the value of MapReduce here is you force the user to express the computation into the parts that can be distributed and completely parallelized, and the parts that can't, that take the results of that. You typically take the results of that and put together a single output. Although obviously it's flexible enough to do that. So what are the challenges of this? Well, there's arbitrary size data. Obviously that's where ZFS comes into play, and we'll talk about how we distribute that. There's arbitrary programs too, right? We want users to be able to run whatever program they have on whatever data they have. That's the whole point of the system. Which means the abstraction is not like a Java program or some narrow JavaScript function or something, as in many cases. It's actually the OS itself. You write a program and you can fork, you can exec, you can read, write, you can open files, you can create temporary files, you can open network sockets, you can do whatever you want. the operating system itself is the abstraction. That's important as well. For the parallelization abstraction, we chose MapReduce because we felt that was a very good, natural way to express the parts of the computation that are distributed and the parts that are not. And the other thing that was important for us in building this system is that it be multi-tenant. We're going to be running this as a public cloud service. So it's really important that like competitors are able to store their objects in the same object store and run their own analytics on them and not worry that like they're going to see the other guy's processes or the other guy's going to see their programs running or their data or something like that, right? We want this to be a fully multi-tenant system. Okay, so now the storage part of the problem. This is what I alluded to earlier. NAS is nice, right? People like a file system. A file system interface is something that programs already know how to deal with. But there's a huge problem with that, which is when it comes to CAP. How many people here are familiar with the CAP theorem from distributed systems? So the CAP theorem, which is a proven result, is that in the face of partition, it's expressed in a lot of different ways. The way I like to phrase it is, in the face of a partition in a network, a distributed system can choose to be strongly consistent or highly available. And it has to choose. You actually can't have both. And a file system interface and NFS pretty much is strongly consistent. You know, there's some client-side caching and there's some things that can happen, but basically it's strongly consistent. Which means that if you do have a partition that's unavailable, and that's not necessarily a terrible trade-off, but the important thing to consider is that most applications that are written in this way for NFS are not built with the idea in mind that, you know, a stack syscall is going to just like go out to lunch for 10 minutes, or the server is just going to potentially go away. And when you're building a distributed system in the cloud that is not supposed to have any single points of failure, it's really not, you know, a whole data center should not be a single point of failure, this becomes kind of a huge problem. At the same time, as we said, the file system abstraction is obviously very useful, right? Programs like grep operate on files. It would be nice if we could just run grep. That was kind of the point. So what we ended up doing was something that incorporates a little bit of both of these results. Object stores are something that look like a file system, but very importantly, they do not allow partial updates. So an object store, which has been popularized with S3, I'm not sure if you're the first to do it, but certainly the most popular one. It's an HTTP-based system, it's key value-based, and it's put get delete. So put some giant blob of data at this path is exactly what a file system does, right? Get this whole blob of data from this path and delete this thing. What it doesn't have, that file systems do have, are the ability to like write to the middle of the file. There's no way to do that, which actually helps a lot. This constraint, which is actually fine for a lot of applications, means that resolving conflicts is much easier. All you have to do is be strongly consistent in the metadata tier, which it turns out is a lot easier. And that allowed us to use ZFS on the storage tier, which again I'll talk about shortly, without worrying about, like, well, what happens if there's two clients writing to different parts of this file on two different ZFS file systems and two different data sets. That just can't happen. Okay, so, and obviously no volume management. What I'm talking about here is not you don't have to manage the physical resources that you're dealing with. You don't have to create shares of NFS with a certain fixed size. Obviously, something ZFS people are very familiar with storage. This has an important implication for us, though. Actually, our design constraint that we want to be able to run programs on this stuff, user programs on these objects, has an important design constraint, which is that the objects themselves are stored as files, just plain files. A lot of other distributed file systems out there, they'll divide the file into a lot of blocks. They'll do erasure encoding, they'll do some kind of redundancy, and spread the blocks across a lot of different systems. That precludes you from being able to do like grep, because you can't run grep on a bunch of blocks on a bunch of physical systems. Right? You actually have to construct it at some point. So we actually store the objects as contiguous files. The other piece that's been really necessary for this, and I apologize for all the background, but I'm going to be getting to the ZFS specific bits very shortly. The other piece of this, which is really important, are the OS containers. How many people here are familiar with zones on Lumos? Actually, how many people in the room are deploying ZFS on Lumos today? I'm just trying to get a rough sense. Okay, as opposed to, say, Linux, ZFS on Linux, okay, and BSD. I think several hands went up several times, which is awesome. Cool. Okay, so at least the Lumos crowd, I imagine, is probably somewhat familiar with zones. Zones are a strong form of OS isolation. It's been in production since 2005, and it's kind of a holistic notion of an OS container, rather than being a bunch of different namespaces, like a paid namespace and a networking namespace. It's a holistic thing, and the kernel knows about this thing in the same way that it knows about threads and processes and things like that, which means it's very strong, right? If you're root in zone, you can't like accidentally remove the box because we didn't think about that namespace that we forgot to isolate, right? It's baked into the kernel. This is a critical piece of infrastructure for us for Manta because We want you, again, the whole point of this thing is to run your program inside our cloud. And actually, maybe I didn't really make that clear already. The point of this is actually to be able to run your programs not just like by downloading all the data, running your thing, and then like uploading the results back to Manta. The point is to actually take your computation and run it inside Manta without copying the data around. In order to do that, we need a safe environment in which to execute arbitrary programs. And that's what OSFP can give us. So obviously, I've been talking about this for a while. Let me just do a quick demo just to show what this looks like. Is that legible? Probably needs to be bigger. Is that legible? Maybe be bigger? A little bigger. So we created a set of command line tools that look a lot like the Unix tools. So I have MLS, which is like LS. This is like listed in my home directory, and then back on Wi-Fi. Obviously, output looks a lot like ls-l, which is the point. Because it's a kind of a distributed macro demo, I sort of have to use Shakespeare, corpus of Shakespeare as my example is then. So under Manta public, we've got examples, Shakespeare. I'll just blend them all. It's the Wi-Fi. So mget is this command that just gets the contents of this thing that's there. I can use input to save data. And then either. So the point of this thing is it's supposed to look and smell a lot like a file system. But right now you can't actually just like open these files. But what you can do is you can run commands on these things. So Shakespeare. So I'm going to list all the files in there. And now I want to do just count how big each of them is. So this command, I'm creating a job that's going to run inside Manta, and it's just going to run WC on all these files. So let me kick this off. -O means to wait for it to complete and then dump all the output. So when I ran this, what Manta did was it took my command, which is WC of my input file, and it located all the 42 objects that are there, and sent requests to each of the servers that are storing those objects saying, I want you to run WC on this and give me back the output. The outputs were saved back into Manta, and my command line tool basically went and fetched them all. Make sense? And obviously, so more concretely, when it runs my command, what it actually does is effectively builds a zone around that file that's stored on ZFS. And then I can run whatever I want in my WC script could be a custom C program that spits all of the bar temp, it does rm minus rf of opt, or whatever it is. At the end of it all, we tear down the zone and we do a ZFS rollback of the file system, which is obviously, I mean, it's a very simple thing, but it's actually extremely powerful ability to do that. And just for completeness, I have here a demo. This is McIlroy's script for word count applied to the Shakespeare corpus. I should have run earlier, but give me a second. So this is exactly McIlroy's script. I've broken out the part that was mapped and the part that was reduced, and I had to put an thing in the middle that actually made that work. And here's the result on Shakespeare. And the point of this is that it's arbitrarily scalable. So we can add more servers to Manta to make that distribute. That will parallelize the computation more. All right, back to the slide. So that's Manta. In terms of the implementation, the main bits that you need to understand for the rest of this talk are the metadata tier, basically a Postgres database using synchronous replication from a primary to a synchronous peer. And the storage tier are just a bunch of dedicated servers running ZFS and zones with Nginx as the communication between that and the rest of the system. So when you do a put to Manta, it's quite simple conceptually what's going on. We do some validation on the path that you gave us to make sure that's legal and you can write to it. We take your data stream and we just select 2 storage nodes at random, blast the data at those nodes, wait for them to get or give us a response, and then once they give us a successful response, we update the metadata tier and we're done. We'll give you the 200 back. In terms of consistency, it's just like last one wins, effectively. And so there's no question of like, if you and I are modifying the same object at the same time, you can't, like one of us is going to win, and whoever is making requests in the middle will see either the old one or the new one or the newest one if there are multiple changes. But there's no question of like resolving conflicts because it's just last one in this case. In terms of using ZFS in Manta, there are kind of I divided into four main categories here: deployment, storage, compute, and metadata replication. I want to start with deployment. The first obvious thing is that we deploy all of the components in Manta as they are also running in zones, and we deploy them with what we call images. This is very similar to what Docker is doing, and I know there's a lot of hype around Docker, and there's a lot of anti-hype around the hype around Docker. But there is something really exciting about this, and I can tell from having used it for a while in an admittedly much more clumsy model. This idea that when we do a build, so all of our repos, when a developer pushes to a repo, we build all the binaries for that thing. We slot it down on top of a pristine ZFS base image, take a snapshot of that. That becomes an incremental image, and then we dump that into a registry that we use for deployment. When you go to deploy it, you're like, okay, well, here are all the versions of all the components, and we want to actually deploy that thing. You just send those ZFS dataset strings over to whatever system you want to deploy it on, and receive them, and now you have all the bits exactly as they were intended to be. So it's a very nice model for deployment. It's exactly what Docker is popularizing, and it's a very compelling way to do it. So importantly, the images are just data sets, and some metadata as well. And most of ours are delivered as incremental changes from a base image. And our Smart Data Center platform, which is what Manta is built on top of, takes care of distributing this. And you say, I want to provision this component on this system, it goes and makes sure that the requisite base image and the incremental images on top of that are over there. Also important here is that if we decide actually this Postgres database needs a bunch more disk space or something like that, we just like ZFS set quote equals whatever on the file system for that zone, and that's very easy to do. Okay, for storage, this is one of those slides that's like, it's ZFS 101. I know everyone here knows all these things, but I think it's really worth pointing out how powerful this really is. We built a distributed storage system without ever writing code to deal with saving bits on disk. I don't know if that's actually been done before, because most of the time, with a lot of the systems that are out there, people want to kind of re-implement the whole storage part. But we knew that ZFS had a solid storage there, right? It's copy on write, the file system is always consistent. It's RAID Z2, which is very economical for us. We've got checksums on all using data on all data period. The ZIL device, I mean, just the fact that we have that is so valuable for us because, as I mentioned before, the time to sync data out to disk is directly seen by the client because we can't tell the client that we actually received their object until the data is stored on both of those systems disks. The fact that we have ZIL there allows us to run the pool much more economically. We don't need a very high IOPS pool in order to get really good latency for our clients. So anyway, I'm well known to everyone here, everyone knows all these things, but really valuable for us. In terms of compute, I alluded to a lot of this before. User tasks get their own zones with their own file system. And we run with 128 zones per system. We do that because our basic idea about scheduling is, hey, the kernel is actually really good at scheduling, so we're just going to throw as much work at the kernel as possible and not queue outside the system. Allow the kernel to deal with CPU saturation, which it does very well. So that's why we have 128 zones per system. These are 256 gig DRAM systems, and it's like 7 terabytes of usable storage. So these are pretty big systems. They can run kind of a lot of stuff. But another key thing here is that we want, when a customer comes to us to run a workload in Manta, we want the software that they want to run to already be there, if at all possible. So if people are doing video analysis, we want FFmpeg there. If they're doing image transcoding or conversion, the image manipulation software should just be there. Image magic should just be there. What that means is we basically have every package installed. So we have 9,000 packages installed, and they use 36 gigs of disk space. So the fact that we have these, we have one copy of this and run it 128 times is also really huge. Again, it's like ZFS 101, but these things are really huge for us. And again, a user, so a lot of these MapReduce computations will end up using a lot of scratch space. Sometimes we need to do a big sort, we need to go to disk for that. We give you a certain amount of scratch space to begin with, but you can ask for more. You can pay a little bit more for a little bit more. And we just implement that as like ZFS set quota equals whatever you ask for, assuming we have it. And actually, if that fails, we know we didn't have it. Again, it's like cold storage, data set management, basic ZFS features, hugely valuable. And I already talked about this, but the users can basically do whatever they want, crap all over the data set, and we know that when it's done, we halt the zone, kill all the processes, run mounted everything, ZFS rollback, and back to a pristine state.
That whole process right now takes about 15 seconds, most of which is our setup scripts during shutdown, and they're just figuring out what the network interfaces should be. We haven't optimized that very well, but we're able to turn around those zones very quickly, and also we keep them ready for you, so when you go run a computation in Manta, you're going to wind up in a zone that's already ready for you, and yes, we turn around quickly. Went back over the logs. I actually used a Manta job over all of our logs, which are also stored in Manta, to count how many rollbacks we've ever done. And we'll get to about 16 million, which is about what I would expect, about 2 per minute on average. I'm kind of curious how this compares to what's been done out there. It's like, I kind of assume that most people are not doing that many rollbacks. But, yeah, most people are not automating it in quite that way. We run a job that's like over 1,000 log files in Manta. We may end up doing, actually we could end up doing 1,000 rollbacks. Okay, so speaking of that, I want to talk about one of the issues that we did run into on this, and it's important to emphasize as I talk about this that we did do 16 million rollbacks, and it turned out that a couple of them didn't quite go as they should have. So the way this played out was that in July of 2013, we saw our first panic in Space Map sync, and then we saw a couple of more panics through December. We had like 2 in September, I think maybe 1 in October, and then like 1, and then December. I believe, Brian, was it Christmas Day?
It was Christmas.
Christmas? Right, I accidentally caused Brian to recall some really bad memories. On Christmas Day, one of these boxes ended up going into a panic loop. It was actually, it panicked on this corruption and then was not able to come back out again. Because when it tried to import the pool, it panicked again. And this turned out to be space map corruption on disk. We were eventually able to get this system to boot. I think we rolled back to a border platform on that one. And then very similar thing happened again on New Year's Day. New Year's Eve, yeah. Yeah, we had some colorful names for these systems. This actually was the same system both times. This problem got progressively worse, and obviously became more and more important to understand what was going on. Eventually, one other machine entered the panic loop, and about 10 others, which was most of the rest of our fleet at the time. Once we discovered this corruption, we figured out how to locate it. We actually found that many of these systems had experienced this corruption, just like weren't at the point where they were panicking that we would get. Some amazing help from Matt and George, and I can't tell you how appreciative we are for the help that you guys gave us on this. Keith was able to build some tools for analyzing the corruption, and eventually we did develop a fix for this. It was a really dark time for us, because there was a couple months there where we were like, again, we built this distributed storage system, and we were like, well, the last thing that's going to be the problem is ZFS, right? And to be clear, at no point in this process were we like, oh man, if only we'd been on UFS, or like, not even a question. And another thing that's really important to remember is when we came back up, we finally fixed this problem, and we scrubbed the pools, and I don't actually think that there was any corruption repaired. I think this turned out to be purely limited to the metadata, but I have to check the notes to be sure. We knew at that point that like no user data was at risk, and had ever been at risk. Which is actually a really important thing to say at the end, right? Data corruption, data loss are the worst things that can happen for a storage system. And in an industry built on trust, it's really bad. Like storage is a trust business. So it's really valuable that we're able to say, actually, we know for a fact that all these files are right, because we have checksums in all of them. We've gone over all the checksums for the scrub, and we're fine. There was another problem we continue to run into rollback, much less severe. We see this issue, it's very streaky. It's, we've seen this probably, we'll see it like 4 or 5 times in a week, and then we won't see it for a couple of months. And actually, I think Brian and I were talking, we might actually, as part of the hackathon, basically like debug this. This might be our hackathon project. What's interesting about this from my perspective, I spent most of my time working on the upstack stuff in Manta, that is the distributed system built on top of ZFS, and it survives OS panics really well. Like if an OS goes away, like we're very good about saying, okay, this guy's gone, we're going to take this computation that was scheduled to run there, run it somewhere else, we're going to redirect the gets from somewhere else. But we don't deal very well with our hangs. And we've had a number of them, mostly not in ZFS. And they're not, when I say a number, it's not like this has been plaguing us, but there have been a couple of different failure modes that result in the operating system hanging in some way. The rollback hangs, or the zone boot hang, the boot or halt hang. It's a much more difficult system, failure mode for a distributed system to deal with, I think. I think there's this tendency to say, well, you just have timeouts on operations and you just like retry it somewhere else. But the other thing is running the same code. So if it's related to the workload, which in our case it almost always was, then you just end up having a hang over there, which is not very helpful. You can also be like, well, okay, I have a hang here and I'm not making forward progress on these rollbacks. Maybe I should panic. Because I know that panicking is fine. The system does well with panicking. It doesn't deal with all of the fleet panicking at once, actually. It is designed to survive several failures, but not 100% failure. So that doesn't necessarily work that well either. This is something that we have to continue to figure out better solutions for being more resilient to. We do Descript for gathering more data on this particular issue, and it almost never happens when the Descript is in place. This is definitely like a very small event. Okay, so those are some of the issues that we have run into around using ZFS rollbacks and stuff like that for computation. How am I doing on time? Close, okay. One other thing I wanted to mention, we also use ZFS for metadata replication. So we're using Postgres for synchronous replication from a primary to a synchronous peer. In the event that the primary crashes at that point, we want to bring up the synchronous peer, but it needs to connect to someone else to be the new synchronous peer. That's what we call the previously asynchronous peer. And for that, we actually, to bootstrap those systems, we use ZFS send and receive. So it's another sort of like bread and butter ZFS. This is hugely valuable for us. So the key takeaways for us are, Unix loves big data. This system has been very successful for us for being able to run, like the thing that I was just describing, like a rep on our tens of thousands of log files. And it was like 80,000 log files looking for the number of rollbacks. It was like an ad hoc query, took like a couple of minutes, not that big a deal. And the second point is actually the one I want to highlight, which is we did build this multi-tenant distributed storage system without ever worrying about the disk on bits, this bits on disk problem. Or maybe I shouldn't say worrying about, but certainly writing code to deal with. And the pooled storage model has been really key for us for this notion of transient OS containers. And this is something obviously the Docker community is really excited about, and we're really excited about as well, and also in terms of Docker. And I think we're going to see a real uptake in that specifically. There's an open pull request for ZFS support in Docker, and figuring out exactly what that looks like is going to be pretty clutch, because it could be really compelling. Just a couple of thoughts about what we'd like to see from ZFS. Actually, the biggest thing for us has been not that this has been a problem. The biggest thing moving forward for us is continued stability, because we are FCS quality all the time. This was mentioned earlier. We will take bits that were basically like just pulled in from Windows yesterday, and we'll end up deploying them in production tomorrow. And that does happen pretty frequently. So we do expect that the repo that is there is working and has been reasonably tested. And yeah, it's basically working. So this is hugely important. So moving forward with some of the things we were talking about, like having a separate upstream repo, it's really important to get these mechanics right so that we can continue to deploy systems built on master. I thought it was pretty interesting that I think it was the ZFS on Linux model that actually had the same criteria, basically. Like every fix is expected to go in complete. It's not like you branch for dev for like 6 months and then you're like, oh crap, now we've got to go fix all the bugs we introduced before release. Actually, everything has to be FCS quality all the time. And that's, there are different phases in a project's lifetime where that's more and less tenable. When something's brand new and immature, obviously that's less tenable. But when you have something that's stable and in production, it's really important that this be the case. And so that's kind of the biggest thing for us. Another thing that was sort of alluded to earlier, which I think would also benefit us a lot, is the hardening of the ZFS receive and import and ZPL import paths. This is not based on data, so we haven't actually looked at this and said, oh, this is just like totally broken. It's just like looking at the code paths, there do seem to be some cases where we're assuming more about the data that comes off on disk than we would like, specifically because naturally the design center, I think originally was like, the enemy is not modifying your disks. In this case though, we would like to allow people to store like a ZFS dataset stream in Manta and then receive it into a dataset and do cool stuff with it. But in that case, the enemy actually is writing that stream for us. So we do actually need to consider those problems. I wouldn't say it's a super high priority issue for us, but it was mentioned by someone else earlier, and I think it would be really interesting. So that's probably about all the time for that. I have a couple of questions. Yeah. Cool.
Okay. You said you one time saw a review or keep panicking on the import.
Yeah.
You said it was for space maps, not for. We've seen in an older version of OS, which is possible got fixed by what you guys did. would see corrupt ARC?
Interesting. I don't know if we did that one. You, Brian, did that ring a bell?
Space out corruption is very specific.
Yeah.
They were trying to keep about this kind of rescue the system. I wonder if you could see ARC stuff as well.
I don't remember any, but I have to go look. So the question was whether we'd seen any issues with panicking on with respect to the ARC. I don't think we've run into anything like that. Space Map one is pretty specific. Brian.
This data system, that's terrific. Is it open source at all?
Good question. So we just open sourced Manta and Smart Data Center last week, and so it's all on GitHub now. It's exciting for us. Yes.
Okay, Postgres related question. So, be really kind. You got your data, you got your metadata, right? So you got your metadata stored in Postgres. Okay.
Yes.
So that means you've got a process running a user space, a user-led process that controls data. What? All right.
Metadata?
Postgres runs the controls that tells you where everything is. So when
Yes.
Postgres goes, you use everything.
Yes.
Okay. Tell me about the Postgres system.
So Postgres is we run it typically with 3 peers. So we have a primary, a secondary, which is a synchronous replicating peer, and then an async peer. So the primary is replicating to the synchronous peer, which means that no transactions are committed to clients from the primary until they have a sync disk on the synchronous peer. Does that make sense? And that's for durability. That's not for availability. It actually reduces availability because it means that if the synchronous peer goes down or the network between them goes down, then they're unavailable. We have a system built around this called Manatee, which is also open source last week, which uses Zookeeper for consensus to basically figure out what the topology should be for replication. And the idea here is if the primary goes away, we want to automatically reconfigure the cluster so that the synchronous peer, which we know is up to date, is now the primary. And the previous asynchronous peer is now the synchronous peer. And so we're replicating from what was from basically from 2 to 3, and 1 is going to have to come around and become an asynchronous peer sometime later. So the idea is that the system should, so this is for availability. This is so that the system survives failures of the individual Postgres components and maintains availability after this cluster reconfiguration. Did that answer your question?
Yeah, it helps me all the way. Okay, so if you got Postgres, you've got a disaster, you get a data structure for whatever reason. Are you does Postgres have rollback capabilities that you use with CFS?
So you said the failure mode there that I'm not sure I understand. That's the Postgres database is corrupted.
For whatever reason, normal traditional database network.
Okay. Like
Are
accidentally
you
drop tables?
recovering using normal standard Postgres methods, or are you taking advantage of DFS? You have a snapshot of the previous version that you took 15 minutes ago to go back to that.
Yeah, so we certainly do have those we take snapshots periodically, and we also do that to catch up the new asynchronous peer. Like if we deploy a new one, we catch up that, right?
It's the only way to do it.
Yeah.
Take a step forward.
Yeah. We also save those back to Manta, but we also keep a copy on the local system. So in the event that we did have that kind of corruption, we could presumably roll back and remove some user data if we did that. That's not happened, so I don't have a lot of operational experience with it.
Okay, so if you have Postgres, then how many processes are going into Postgres that manage everything?
You mean how many clients, like outside of Postgres?
Basically, you're going to have client processes.
Yeah.
You go into Postgres, it's updating the management of metadata, it's referencing the metadata, it's doing everything there. How many
Yeah.
processes? Can you answer the full question?
So that's a good question. So we run Postgres with 1,000 worker processes, which means we can have up to 1,000 client instances. We're using Node.js, so they don't necessarily map to processes because we're using the event concurrency model. So we may have a single process that's actually got like 50 database connections over. So, but I think that's what we were getting at, was the number of database connections. And we use a layer we built on top of Postgres called More, which I didn't get into it all here because it was less interesting from the ZFS perspective. But More is a key value store built on top of Postgres that also knows about the replication topology from the Zookeeper side. So I said that basically,
They're using a caching layer.
well, it's not caching, but it's caching database connections, yes. It's not a data cache, but it's caching the database connections. I think I'm basically out of time there, right? I can take questions offline while we're around. Sorry.
This is really quick, Pat. How
Yeah.
long does it take to get these compare back to this after that happens?
Definitely on the order of like 2 or 3 minutes, but most of that is actually, it's probably a lot less than that. That's like,
That's a lot.
okay.
Thanks a lot.